question revolves around the application of NEC Section 240.4b concerning the protection of conductors against overcurrent. Specifically, it deals with the three-phase 208 volts 1200 amps service. The initial setup involves 3 riser conduits, each containing 4 600 kc mil conductors running from the current transformer CT to the overhead drop. From the CT to the 1200 amps main breaker, the contractor installed 3 sets of 4 500 kc mil conductors. The concern raised is whether this configuration violates NEC Section 240.4b. NEC Section 240.4b typically mandates that overcurrent protection devices opt to protect conductors according to their ampacity. However, there are exceptions, particularly in switchgear assemblies with multiple switches and no single main switch. The key consideration is whether the load calculation dictates the conductor size, overriding the usual overcurrent protection rules. The initial reaction might be to apply 240.4b. However, when considering switchgear where the required number of overcurrent protective devices is present, the situation changes. Load calculations following Article 220 become crucial in determining the appropriate conductor size. Clarification regarding the application of 240.4 is essential in these scenarios. If there are 6 or fewer switches without a main switch, the provisions of 240.4 may not necessarily apply. According to the handbook, Exception Note 1 states that switchboards and panel boards with main overcurrent devices not exceeding 600 amps shall not require such series or parallel connection. Therefore, in a service with 3 switches, the provisions of 240.4 might not be mandatory. In such cases, the primary requirement is that the conductor ampacity is sufficient to supply the calculated load. The exception to 240.4 permits a departure from the standard overcurrent protection rules when dealing with switchboards and panel boards meeting specific criteria. The rationale behind this exception is that the overall system design, including load calculations and the number of overcurrent devices, provides adequate protection. It's important to understand the nuances of this exception to ensure compliance with the NEC while optimizing the design of electrical services. Let's delve deeper into the relevant sections of the NEC to fully grasp the principles at play. NEC Article 220 provides comprehensive guidelines for calculating electrical loads. These calculations are crucial for determining the appropriate conductor size and the rating of overcurrent protection devices. When applying the exception to 240.4, a thorough load calculation is essential to ensure that the conductors are adequately sized for the anticipated load. The load calculation should consider all connected loads, including lighting, receptacles, motors, and other equipment. It should also account for demand factors, which recognize that not all loads will operate simultaneously at their maximum capacity. Once the load calculation is complete, the minimum required conductor ampacity can be determined. This ampacity must be equal to or greater than the calculated load. In situations where the exception to 240.4 applies, the conductor ampacity becomes the primary factor in determining the conductor size. The overcurrent protection devices must still provide protection against short circuits and ground faults, but their rating may not necessarily be dictated by the conductor ampacity alone. The overcurrent protection devices should be sized to protect the equipment connected to the circuit, taking into account the equipment's ampacity rating and any applicable code requirements. It's important to note that the exception to 240.4 does not eliminate the need for overcurrent protection altogether. It simply allows for a more flexible approach to sizing the overcurrent protection devices in certain specific situations. The overcurrent protection devices must still be sized to protect against short circuits and ground faults, and they must comply with all other applicable code requirements. Furthermore, the exception to 240.4 only applies to switchboards and panel boards with main overcurrent devices not exceeding 600 amps. This limitation is intended to ensure that the exception is only applied in situations where the overall system design provides adequate protection. In larger services, the standard overcurrent protection rules typically apply. In a specific scenario described, the service has 3 switches and a 1200 amps main breaker. The fact that there are 3 switches suggests that the exception to 240.4 might apply. However, the 1200 amps main breaker exceeds the 600 amps limit specified in the exception. Therefore, it's not immediately clear whether the exception can be applied in this case. Further analysis is required to determine whether the overall system design provides adequate protection. This analysis should include a thorough load calculation, as well as a review of the equipment connected to the service. If the load calculation indicates that the conductors are adequately sized for the anticipated load, and if the overcurrent protection devices are sized to protect the equipment connected to the circuit, then it may be possible to justify the use of the exception to 240.4. However, it's important to consult with a qualified electrical engineer or inspector to ensure that the installation complies with all applicable code requirements. It's also worth noting that the NEC is subject to interpretation, and different inspectors may have different opinions on how to apply the code in specific situations. Therefore, it's always a good idea to get a second opinion if you are unsure about the correct interpretation of the code. In summary, the application of 240.4 and its exceptions can be complex and requires careful consideration of all relevant factors. Load calculations, conductor ampacity, and the rating of overcurrent protection devices must all be taken into account. It's essential to consult with qualified professionals and to stay up to date on the latest code requirements to ensure that electrical installations are safe and compliant. Understanding the interaction between conductor ampacity and overcurrent protection is crucial for electrical safety and compliance. Conductors are selected based on the load they are expected to carry, but their ampacity, which is the maximum current they can safely conduct, must also be considered. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overheating and potential fire hazards caused by excessive current flow. NEC Section 240.4b outlines the general rule that conductors must be protected against overcurrent in accordance with their ampacities. This means that the overcurrent protection device must be sized no larger than the conductor's ampacity. However, there are exceptions to this rule, as previously discussed. One common exception is the next higher standard overcurrent device rating rule, which allows the use of the next higher standard overcurrent device rating if the conductor ampacity does not correspond to a standard overcurrent device rating. For example, if a conductor has an ampacity of 22 amps, the next higher standard overcurrent device rating is 25 amps. Another important consideration is the type of conductor being used. Different types of conductors have different ampacities depending on their insulation size and installation conditions. The NEC provides ampacity tables for various types of conductors, which must be consulted when selecting conductors for a particular application. In addition to ampacity, other factors must be considered when selecting conductors, such as voltage drop, dirting factors, and the environment in which the conductors will be installed. Voltage drop refers to the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. Dirting factors are applied to conductor ampacities to account for factors such as ambient temperature, the number of conductors in a raceway, and the presence of harmonics. The environment in which the conductors will be installed can also affect their ampacity. For example, conductors installed in direct sunlight or in a hot environment will have a lower ampacity than conductors installed in a cool, shaded environment. Proper conductor selection is essential for ensuring the safe and reliable operation of electrical systems. By carefully considering all relevant factors, electrical engineers and contractors can select conductors that are adequately sized for the anticipated load and that are protected against overcurrent. Now, let's consider the specific conductors mentioned in the original scenario: 600 kc mil and 500 kc mil copper conductors. According to NEC Table 310.15b16, which provides ampacities for insulated conductors rated up to 2000 volts, 600 kc mil copper conductors with a 75 degrees Celsius insulation rating have an ampacity of 475 amps. Similarly, 500 kc mil copper conductors with a 75 degrees Celsius insulation rating have an ampacity of 380 amps. In the original scenario, there are 4 600 kc mil conductors per phase from the CT to the overhead drop, and 3 sets of 4 500 kc mil conductors per phase from the CT to the 1200 amps main breaker. To determine the total ampacity of the conductors in each case, we must multiply the ampacity of a single conductor by the number of conductors per phase. For the 4 600 kc mil conductors per phase, the total ampacity is 4 conductors * 475 amps / conductor equals 1900 amps. For the 3 sets of 4 500 kc mil conductors per phase, the total ampacity is 3 sets * 4 conductors / set * 380 amps / conductor equals 4560 amps. Comparing these values to the 1200 amps service rating, it appears that the conductors are adequately sized for the load. However, it's important to remember that other factors, such as voltage drop and derivative factors, must also be considered. In addition, the overcurrent protection devices must be sized to protect the conductors against short circuits and ground faults. The NEC provides specific requirements for sizing overcurrent protection devices, which must be followed to ensure that the installation is safe and compliant. One important requirement is that the overcurrent protection device must be rated no higher than the ampacity of the conductors it is protecting. However, as previously discussed, there are exceptions to this rule. One exception is the next highest standard overcurrent device rating rule, which allows the use of the next highest standard overcurrent device rating if the conductor ampacity does not correspond to a standard overcurrent device rating. Another exception is the exception to 240.4, which allows for a more flexible approach to sizing the overcurrent protection devices in certain specific situations. When applying these exceptions, it's important to carefully consider all relevant factors to ensure that the installation is safe and compliant. It's also important to consult with qualified professionals and to stay up to date on the latest code requirements. In conclusion, the application of 240.4 and its exceptions requires a thorough understanding of the NEC as well as careful consideration of all relevant factors. Load calculations, conductor ampacity, and the rating of overcurrent protection devices must all be taken into account. By following these guidelines, electrical engineers and contractors can ensure that electrical installations are safe, reliable, and compliant with the NEC. The main question to ask now is, if the load calculation is less than the calculated ampacity of the wire, is it acceptable? If the calculated load is less than the total ampacity of the conductors, it generally is acceptable from a conductor sizing perspective. However, there are several important caveats and additional considerations to keep in mind. Firstly, overcurrent protection. The overcurrent protection device must still be sized appropriately to protect the conductors from overloads, short circuits, and ground faults. Even if the load is less than the conductor ampacity, the OP should be sized according to NEC guidelines to protect the conductors. This often means selecting an OP that is no larger than the conductor ampacity, unless specific exceptions allow for a larger OPT. Secondly, derating and adjustment factors. Conductors must be derated for various conditions, such as high ambient temperatures, multiple conductors in a raceway, or specific types of loads. The ampacity of the conductors after derating must still be greater than or equal to the calculated load. For example, if conductors are installed in a hot environment, their ampacity may need to be reduced, which could affect the overall acceptability of the installation. Thirdly, voltage drop. Conductors must be sized to limit voltage drop to acceptable levels. Even if the conductor ampacity is sufficient for the load, excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Fourthly, future expansion. It is often prudent to size conductors larger than the current calculated load to accommodate future expansion or changes in load. This can help avoid the need to replace conductors if the load increases in the future. Sizing conductors for future expansion can provide flexibility and cost savings in the long run. Fifthly, equipment limitations. The ampacity of the conductors must be compatible with the terminals and equipment to which they are connected. Terminals and equipment are often rated for specific conductor sizes and ampacities, and these ratings must be observed. For example, if a circuit breaker is only rated for conductors up to a certain size, larger conductors cannot be used, even if their ampacity would otherwise be sufficient. Sixthly, code compliance. All installations must comply with all applicable requirements of the NEC and local codes. These codes may have specific requirements for conductor sizing and overcurrent protection, which must be followed. Code compliance ensures the safety and reliability of electrical installations and helps prevent hazards such as fires and electrical shocks. Seventhly, engineering judgment. In complex or unusual situations, it may be necessary to consult with a qualified electrical engineer to determine the appropriate conductor size. An engineer can perform detailed calculations and analysis to ensure that the installation is safe and compliant. Engineering judgment is particularly important in situations where there are multiple factors to consider or where the code requirements are not clear. Eighthly, continuous loads. For continuous loads that operate for 3 hours or more at a time, the OC must be rated at 125% of the continuous load. This means that the conductor ampacity must also be at least 125% of the continuous load. For example, if a continuous load is 20 amps, the OC must be rated at least 25 amps, and the conductor ampacity must also be at least 25 amps. Ninthly, conductor insulation type. The type of insulation used in the conductors affects their ampacity. Different insulation types have different temperature ratings, which determine the maximum current they can carry safely. The NEC provides ampacity tables for various insulation types, which must be consulted when selecting conductors. Tenthly, number of conductors in a raceway. When multiple conductors are installed in a single raceway or cable, their ampacity must be derated to account for the heat generated by the conductors. The NEC provides derating factors for various numbers of conductors in a raceway. In summary, while it is generally acceptable for the calculated load to be less than the total ampacity of the conductors, it is essential to consider overcurrent protection, derating factors, voltage drop, future expansion, equipment limitations, code compliance, and engineering judgment. All of these factors must be taken into account to ensure that the installation is safe, reliable, and compliant with all applicable requirements. Let's revisit the specific scenario with the 3-phase 208 volts 1200 amp service. We have 3 riser conduits, each with 4 600 kc mil conductors running from the CT to the overhead drop. From the CT to the 1200 amps main breaker, the contractor ran 3 sets of 4 500 kc mil conductors. The question is whether this configuration complies with the NEC, particularly with respect to 240.4 and its exceptions. Firstly, conductor ampacity. The 4 600 kc mil conductors per phase have a total ampacity of 1900 amps. The 3 sets of 4 500 kc mil conductors per phase have a total ampacity of 4560 amps. Both of these ampacities are greater than the 1200 amps service rating, so the conductors appear to be adequately sized for the load. Secondly, overcurrent protection. The 1200 amps main breaker provides overcurrent protection for the service. However, it is important to ensure that the conductors are also protected from overloads, short circuits, and ground faults. The NEC requires that conductors be protected against overcurrent in accordance with their ampacities. In this case, the 1200 amps main breaker is smaller than the total ampacity of the conductors, so it appears to provide adequate overcurrent protection. Thirdly, exceptions to 240.4. The exception to 240.4 allows for a more flexible approach to sizing the overcurrent protection devices in certain specific situations. However, this exception only applies to switchboards and panel boards with main overcurrent devices not exceeding 600 amps. In this case, the 1200 amps main breaker exceeds the 600 amps limit, so the exception does not apply. Fourthly, load calculation. A detailed load calculation is essential to ensure that the conductors are adequately sized for the anticipated load. The load calculation should consider all connected loads, including lighting, receptacles, motors, and other equipment. It should also account for demand factors, which recognize that not all loads will operate simultaneously at their maximum capacity. If the load calculation indicates that the conductors are adequately sized for the anticipated load, and if the overcurrent protection devices are sized to protect the equipment connected to the circuit, then the installation may be considered compliant. Fifthly, local codes. It is important to consult with local authorities and to comply with all applicable local codes. Local codes may have specific requirements for conductor sizing and overcurrent protection, which must be followed. In summary, the configuration described appears to comply with the NEC, provided that the load calculation indicates that the conductors are adequately sized for the anticipated load, and that the overcurrent protection devices are sized to protect the equipment connected to the circuit. However, it is important to consult with qualified professionals and to comply with all applicable local codes to ensure that the installation is safe, reliable, and compliant with all applicable requirements. The question of whether the load calculation dictates the conductor size and switchgear with 6 or fewer switches, without a single main switch, is a nuanced one that requires a careful understanding of the NEC. While the general rule is that conductors must be protected against overcurrent in accordance with their ampacities, there are exceptions that allow for a more flexible approach in certain specific situations. In switchgear with 6 or fewer switches, without a single main switch, the exception to 240.4 may apply. This exception allows for a departure from the standard overcurrent protection rules, provided that the overall system design provides adequate protection. The rationale behind this exception is that the multiple switches and overcurrent devices provide redundancy and protection against overloads, short circuits, and ground faults. In these situations, the load calculation becomes the primary factor in determining the conductor size. The conductors must be sized to carry the anticipated load, taking into account demand factors, voltage drop, and other relevant factors. The overcurrent protection devices must still provide protection against short circuits and ground faults, but their rating may not necessarily be dictated by the conductor ampacity alone. The overcurrent protection devices should be sized to protect the equipment connected to the circuit, taking into account the equipment's ampacity rating and any applicable code requirement. It is important to note that the exception to 240.4 does not eliminate the need for overcurrent protection altogether. It simply allows for a more flexible approach to sizing the overcurrent protection devices in certain specific situations. The overcurrent protection devices must still be sized to protect against short circuits and ground faults, and they must comply with all other applicable code requirements. In addition, the exception to 240.4 only applies to switchboards and panel boards with main overcurrent devices not exceeding 600 amps. This limitation is intended to ensure that the exception is only applied in situations where the overall system design provides adequate protection. In larger services, the standard overcurrent protection rules typically apply. When applying the exception to 240.4, it is essential to perform a detailed load calculation to ensure that the conductors are adequately sized for the anticipated load. The load calculation should consider all connected loads, including lighting, receptacles, motors, and other equipment. It should also account for demand factors, which recognize that not all loads will operate simultaneously at their maximum capacity. Once the load calculation is complete, the minimum required conductor ampacity can be determined. This ampacity must be equal to or greater than the calculated load. In situations where the exception to 240.4 applies, the conductor ampacity becomes the primary factor in determining the conductor size. The overcurrent protection devices must still provide protection against short circuits and ground faults, but their rating may not necessarily be dictated by the conductor ampacity alone. In summary, the question of whether the load calculation dictates the conductor size in switchgear with 6 or fewer switches, without a single main switch, depends on whether the exception to 240.4 applies. If the exception applies, the load calculation becomes the primary factor in determining the conductor size. However, it is important to remember that the overcurrent protection devices must still provide protection against short circuits and ground faults, and that all other applicable code requirements must be followed. Finally, let's address the original concern about a potential violation of 240.4b. Section 240.4b of the National Electrical Code (NEC) generally requires that conductors be protected against overcurrent in accordance with their ampacities. This means that the overcurrent protection device such as a circuit breaker or fuse, should be sized no higher than the ampacity of the conductor it protects. However, there are several exceptions to this rule, as mentioned previously. Given the scenario of a three-phase 208 volts 1200 amp service with 3 riser conduits, each containing 4 600 kc mil conductors from the CT to the overhead drop, and 3 sets of 4 500 kc mil conductors from the CT to the 1200 amps main breaker, the initial concern about violating 240.4b is understandable. Let's break down the factors that would determine whether a violation exists. Firstly, conductor ampacity and size. The ampacity of the conductors and the size of the overcurrent protection device are critical. The 4 600 kc mil conductors likely have a combined ampacity well above 1200 amps, and the 3 sets of 500 kc mil conductors also have a substantial ampacity. If the 1200 amps main breaker is protecting these conductors, it is likely within the allowable limits, especially considering that the conductors are in parallel. Secondly, parallel conductors. When conductors are run in parallel, as is the case here, the combined ampacity of the parallel conductors must be equal to or greater than the rating of the overcurrent device protecting them. Section 310.10h of the NEC addresses requirements for conductors in parallel. If the installation meets the requirements outlined in 310.10h, the parallel conductors are permitted and the overcurrent protection can be based on the total ampacity of the parallel conductors. Thirdly, exception to 240.4 if the service is designed with 6 or fewer switches or circuit breakers and no main overcurrent protective device, the rules of 240.4b may not strictly apply. Instead, the conductor size would be based on the calculated load per Article 220, as long as the conductors are protected against short circuits and ground faults. Fourthly, load calculations. A detailed load calculation is necessary to determine the actual load in the service. If the calculated load is significantly less than the ampacity of the conductors, the installation may be acceptable, provided that the conductors are properly protected against short circuits and ground faults. Fifthly, equipment ratings. The terminals and equipment to which the conductors are connected must be rated for the size and ampacity of the conductors being used. This is an important consideration to ensure that the connections are safe and reliable. Sixthly, inspection authority. The local electrical inspector has the final say on whether an installation complies with the NEC and local codes. It is important to work with the inspector to ensure that the installation meets all requirements. In summary, while the initial thought of a violation of 240.4b is a valid concern, the installation may be acceptable if the conductors are properly sized for the load, are protected against short circuits and ground faults, and meet the requirements for parallel conductors. A detailed load calculation and consultation with the local electrical inspector are essential to making this determination.